Alaikum. My name is Marwan Fatani. I'll be explaining in this video electromagnetic polarization. So a quick overview of what are electromagnetic waves. They are basically waves of energy and they are formed by the oscillating of electric and magnetic fields. They don't require a medium to propagate in, so they can travel through space or air or whatever basically. And they are traveling at the speed of light. They are generated by accelerating electric charges or any change in an electric charge's motion, which is going to emit electromagnetic radiation. Moving on, we are going to go through a simple vector review, and for any vector it has three main components: the x-hat direction, the y-hat direction, and the z-hat direction. But in the case of electromagnetic waves, the z-hat direction is non-existent, and that is because in electromagnetic waves the direction of propagation has no component. Electromagnetic waves has no component on the direction of propagation, and in this case is going to be the z-hat direction. And these are just quick overview formulas of how to calculate the components and getting the magnitude of the vector. So let's talk electromagnetic polarization. What are electromagnetic polarization? Basically, it describes the motion in which the electric field component of a light wave oscillates on the plane. And most of the time, the plane is perpendicular to propagation. It occur in a plane at right angles to the direction the wave is traveling. And we have three types of polarization: linear polarization, circular polarization, and elliptical polarization. In linear polarization, the electric field oscillates back and forth along a single plane. But in circular polarization, the electric field actually forms a circle along the plane. And in elliptical polarization, the electric field forms an ellipse shape along that plane. We're going to have a simulation to visualize all of these motions, but we're going to first go through the case by case for each of these three motions. The first one being the linear polarization. I placed a couple of conditions, let's say, for when the linear polarization occurs. Linear polarization occurs when the electric field components of the x-hat component and the y-hat component have a phase difference of exactly 0 or pi in degree radians or 180 degrees. The amplitudes of the x-hat and the y-hat direction can be equal or unequal, and they're most likely constant. So regardless of the amplitudes, if the phase difference is 0 or pi, the resultant electric field oscillates along a fixed line. Let's show you a cool animation to visualize this. So I'm going to press the start button right here, and you can see this point exactly is the polarization. It's moving on a straight line. And what happens if we make the magnitudes, which are right over here, the EX and the EY magnitude, different? So as I move it around, you can see that the polarization is still linear, but the direction has changed. I can make it purely on the y-axis, or I can make it purely on the x-axis. Now, let's try to change the frequency. I haven't talked about any of the other components that are present in an electromagnetic wave. We have the frequency, the relative permittivity, the permeability. So what happens if we change the frequency, which is right here? Let's place it into, let's say, 1500, random number. Nothing changes. So the frequency does not have any effect on polarization. What about the other components, like the permittivity? Let's change it into 3. Nothing changes. What about the permeability? Let's make it 5. Again, nothing is changing. So the components other than the amplitude and the phase difference does not change the polarization. that is taking place. This is a better visualization of the plane right over here. As you can see, we have a straight line of polarization. Now let's try to change the amplitude of X one more time, and as you can see, we can move the direction of polarization, and if the amplitude of X becomes 0, we have a pure polarization along the y-axis, as you can see right here. And vice versa is also true. If you make the amplitude of Y 0, we have a pure polarization along the x-axis. Now, moving forward, we have the circular polarization. And the circular polarization, just to remind you, we are going to have a circular motion along the plane. So the conditions for the circular polarization, it requires that the amplitude are equal. They must be equal for the circular polarization to occur. The phase difference must be 90 degrees, not 0, not pi, exactly pi over 2, 90 degrees. So under these conditions, the electric vector maintains a constant magnitude and rotates uniformly, tracing a circle. Let's go back to our visualization right here. I'm going to keep the magnitudes equal. Let's change the phase difference, which is right over here. So what happens if I made it 90 degrees exactly? As you can see, tracing back again, it is forming a circle. Okay, let's show it over here by changing this, the X phase of X, exactly to 90 degrees. Exactly as the animation from before, we have a circular path or motion, and let's trace it. Now, what happens if we change the amplitudes? So I'm going to change the amplitude to be different than the amplitude of Y, and as you can see, it's not a circle anymore. And this gets us into our next polarization, which is the elliptical polarization. Let's get back to the slides. So elliptical polarization, we're going to have an elliptic shape, and we have another conditions, or basically, as we talked about the linear polarization and circular polarization, if none of the conditions for the linear or circular happens, then we automatically have an elliptical polarization. It is the most general form of polarization, and it occurs when the amplitudes are unequal or the phase difference is not 0, pi, or plus or minus 90 degrees. The electric field vector traces an ellipse with both its magnitude and direction changing over time. Let's show the outcome on our simulation. And from before, I haven't changed the frequency and the permittivity and permeability because they have no effect on the polarization whatsoever. Let's change the degrees right over here to, let's say, 39, play around with the magnitudes, and we're having a elliptic polarization. So in this case, we have both the magnitudes are different, we have a phase different, and we're having an ellipse shape. Now let's make the magnitudes equal, but the phase difference is still different, and we're still having an ellipse shape. Let's showcase this right over here. So firstly, I'm gonna make the amplitudes and of X and Y equal. We have a circle because they are in a 90-degree phase shift. Now let's make the phase shift not 90 degree. Let's see what happens. It's an ellipse, as you can see. Now let's make the phase difference equal. We get a straight line. Now let's change the amplitude of either X or Y. Let's see what happens with a phase shift. as you can see, it's another ellipse. So in conclusion, the polarization of electromagnetic waves have three scenarios. It's going to either be a linear by having the phase shift exactly 0. We can have a linear polarization. We can also have a circular polarization by making the phase shift exactly 90 degrees plus or minus, as you can see right here. And the last case, we have the ellipse, and that is if none of the previous conditions occur, we automatically have an ellipse, even though it's a 90-degree phase difference, but the magnitudes are not equal, so we get an ellipse. And on top of that, the frequency and the relative permittivity and permeability have no effect whatsoever on the polarization, and also the wavelength, because if we change the frequency, the wavelength changes a bit. So let's make the frequency 200, for example. The wavelength just increased and no change on the polarization. Into a little bit more details, we can look at the right hand or left hand polarization for the circular polarization. The right hand polarization is basically the direction of rotation of the polarization, if it is clockwise or counterclockwise, and is going to depend on the phase difference, if it's positive or negative. Of course, all of this is based on that you're looking towards the source along the wave's propagation direction. So for the right hand rule, looking at the source of propagation, you point your right thumb in your direction and then you curl your fingers, and that is the electric field's rotation, which is clockwise. And for the left hand is going to be the opposite. As you look at the propagation direction, you point your left thumb in your direction and your fingers will curl in the direction of the electric field's rotation. And again, to show it in a simulation, as you can see right over here, we have a left-handed polarization because the phase difference is actually negative. We change the Y phase. So let's show it one more time. The phase difference are right now equal and we have a linear polarization. Let's change the phase of the Y component to 90 degree and we have a left-handed polarization. Now if you point your thumb right now towards you, you can see that the direction is in the direction of the rotation. And if we change the phase of the X component to 90, making it a positive change, positive 90 degrees phase difference, we can see that it is a right-handed polarization. And to finally conclude the video, we are going to look at the mathematical form, and I made a simple summary table to showcase all the different polarization types. We have the first one, the linear, and the phase difference is 0 or pi, and the amplitude is equal or unequal, and the electric field expression, as you can see on the right hand side, the field expression, we have only one cosine component because there is no phase difference, so there is no sine component on the mathematical expression. But on the circular polarization, we can see that there is an x component and there is a cosine and a sine to showcase the phase difference. And you can also notice that the magnitude is not ex and ey but only e node, because the magnitude in the circular polarization does not change. And lastly, for the elliptical, we have an x component and a y hat component, an x hat component and y hat component, a cosine components. We have the phase difference component, and we have a e node x and e node y, because because both of the amplitudes could be different or equal. Both of the phase differences can be as random as it can be. Thank you very much for listening. I hope you learned something of value from this video, and thank you very much.